Section 3 takes what we learned in the last section about Boyle's and Charles' laws, and it adds a mathematical component. Today we're going to be graphing gas behavior. The objective that goes along with this section is to construct and interpret graphs representing both Charles' law and Boyle's law. So before we jump into how to graph those two gas laws, let's just do a quick review of what is a graph. So a graph is a diagram. It's an image that tells us how two variables are related to one another. And you studied variables quite extensively last year when you were doing your science fair project. Remember, a variable is anything that can change in a science experiment. And in a good experiment, we're going to have two, if not three, very distinct or specific types of variables. We'll have our controlled variables, which are the variables that don't change. Those are the things we're going to keep the same in order to have a better understanding of the purpose of the experiment, the question, the hypothesis. And then there are also dependent and independent variables. An independent variable is the variable that is changing in an experiment. That's going to be one of the variables that runs along an axis on your graph. The other variable is the dependent variable. That's what changes as a result of the independent variable, of the thing that changed. So if time is my independent variable, then the dependent variable would be that my hair gets really long. The longer the time, the result without a haircut is my hair gets long. Graphs are tools, and we can use them to make predictions. If I were plotting my example, my time over how long my hair is example on this graph, I would probably, after a series of days or series of weeks, start to notice patterns in my graph. I could use those patterns to predict how long my hair might be if I allowed it to not be cut for an additional 2 months. The gas laws are all about relationships as well, which is why graphs work so well in predicting and interpreting gas behavior. Here's a series of images. These were in your textbook, so you've already had a chance to see them once. This is an experiment that is designed to show the relationship between temperature and volume. And hopefully when you see temperature, you start to think Charles' law. Temperature and volume, the relationship there is Charles' law. So in this experiment that they were showing you, they had a hot plate, and then on that hot plate, a beaker with a metal cylinder. Now this picture is cut away so you can see what's inside the cylinder. Basically, there is a piston which is stopping the gas, trapping the gas beneath it, and then there is a set volume of gas to start with. In this case, we are starting with 50 milliliters of gas inside of this cylinder with the piston holding it down. Around the outside of the cylinder, there's an ice bath. So basically a bunch of water with ice in it to cool it down to 0 degrees Celsius. So to start the experiment, we have a hot plate that's not turned on yet. We have a beaker with a cylinder that's trapping 50 milliliters of volume of gas inside of the cylinder. And then around it, keeping all that gas at a nice cool temperature of 0 degrees Celsius, we have an ice bath with a thermometer that's helping us to track that temperature. Now, if you look over at the data table that's right next to the picture, you'll notice that in this experiment, all the scientists basically did was turn the hot plate on. And then the scientist watched two different readings. The first reading he watched was the thermometer. And so every 10 degrees Celsius, he made sure to document, and he also watched the volume of the gas. And you'll notice that the volume of the gas is still expressed in milliliters on the data table. And the volume of the gas, it looks like, goes up every time that the temperature goes up by 10 degrees Celsius. Now there's a third column. There's a column in the middle that's labeled with a K. That K stands for Kelvin. The SI unit for temperature typically is thought of as being Celsius, but sometimes to make math a little more simple and to standardize even just a little bit more, scientists will take temperature measurements not even in Celsius, but in Kelvin. Kelvin is a really easy temperature to convert to if you're starting in Celsius. All you need to do is add the number 273 to your Celsius reading. So if you started with 10 degrees Celsius, add 273 to that, Your Kelvin temperature is going to be 283. Now notice also that there's no degree symbol after Kelvin. It's 273 degrees Fahrenheit, 273 degrees Celsius, but just plain old 273 Kelvin, no degree with the Kelvin label. And so over time, the scientists allowed the temperature of the water on the hot plate to go from 0 degrees Celsius to 100 degrees Celsius. As he was tracking at 10-degree intervals, he was also tracking the volume. And then after the fact, he converted his temperatures into Kelvin. Now we have all the data that we need. It's time to make our graph, right? Graphs in science are going to be set up using a pretty succinct set of rules. So the rules aren't going to change very often. We have our two axes on our graph, right? We have our x-axis and our y-axis. I like to try to remember the two or tell the two apart by thinking that a y dips up and down. It's got a longer stretch that runs vertically up and down, so that's going to be the x or the y-axis. It runs up and down. The x-axis, everything's even side to side, so that runs the other way, runs perpendicular to the y-axis. When you're looking at your axes, you're going to label always using your manipulated variable or your dependent variable along the bottom, the x-axis, and your responding variable, your independent variable goes along the bottom, and your responding variable or your dependent variable is going to go along the y-axis. It's important to always remember to put your units onto your graph. So in this case, our manipulated variable, our independent variable, was temperature. That was being changed, and then as a result of that, the volume also changed. We had the hot plate to manipulate our temperature, but because we were doing that, the volume of the gas inside that piston, inside that chamber, started to go up. So the manipulated variable would be temperature in Kelvin along the x-axis, and the responding variable would be volume in milliliters along the y-axis. Here we see that graph all plotted out, and we notice that Charles' law shows that the volume of a gas is directly proportional. It means it's going to run the same way as, behave the same way as the temperature of the gas under a constant pressure. When we say directly proportional, again, we are describing a relationship between two variables. You're going to be able to see if something is directly proportional just by looking at a graph, because you'll notice that that line that the graph makes runs straight through the 0, 0 point. So here we could draw our line starting at 0, 0 all the way in a straight angle through to what would be the end of the graph, 400 degrees Kelvin, or 400 Kelvin, and something in the range of 74, 75 volume in milliliters. Our second example in the book was all about pressure and volume, and hopefully when you think pressure and volume, you're starting to get a sense of Boyle's law. Boyle's law has to do with how pressure and volume are related in a gas. Here, you'll notice that the experiment also involved the cylinder with the piston because we have to measure volume, but we're also, in this case, measuring pressure. And so that's that little gauge that you see off to the side measuring in kilopascals. Kilopascals is the SI unit for pressure. And so what's happening here is that you have 100 milliliters volume of gas inside of the cylinder, and the pressure being placed on that gas to start is 60 kilopascals. Now slowly the piston is going to be pushed into the cylinder. It's going to be compressing the gas, adding pressure. And as the pressure of the gas, or as the volume of the gas, decreases by 90 or 10 milliliters, so from 100 to 90, then we're going to measure what happens as a result to the pressure of those gas particles in the container. So we're controlling the volume. We're very slowly pressing down so that the volume is going down by 10 milliliters every trial. The pressure is going to respond as a result. And when we graph our results from this experiment on a graph, again, we have our independent variable, our volume, that's the one we're controlling along the x-axis, and we have our pressure, that's the responding or independent variable, or dependent variable, along the y-axis. We see a downward slope running from left to right. So Boyle's law, if we look at the graph, shows that the pressure of a gas varies inversely or is inversely proportional with its volume when we're dealing with a situation where there's a constant temperature. So inversely proportional, again, is a term that's used to describe the relationship between two variables where they're basically opposite of one another. And you're going to notice an inversely proportional relationship on a graph when you have a line like the one you see here. The graph is going to form a curve, and that curve slopes downward. Your homework for Friday is going to be to complete the 2.3 open note quiz. You will be asked to do a little bit of graphing on your quiz, and then I'd also like you to take a look at and to start your 2.4 notes. I know we're moving really fast through all these sections, but there's so much good stuff to get to. I'm going to try to get through as much as possible before the end of the year, so you're really prepared when you get into high school. Let me know if you have any questions, and I'm always here to help.